yeah, if you guys, like I said, if you guys want to, you can open up the slides. The slides that we're going to be looking at are slides 56 to 58. And then I'm going to do some example problems. Looking at the different worksheets. The worksheet should be on Google Classroom. And so if you want to, you're certainly welcome to look at that. I'm going to be hopefully linking up to this iPad, so hopefully you can see the screen just like last time. But either put it in the chat or you can just ask the questions here. Last time we looked at being able to determine the states, whether something is aqueous or solid. I don't know, does anybody have any questions about that?
Nope.
Right on. So if there aren't any other questions, I'm going to do a little bit of a recap just because you need it. Hopefully, when I share the screen, hopefully it will come through just like last time. We'll see. Of course, it doesn't work. Good job. All right. All right. All right. So hopefully you guys can see the screen that I'm on. That's true. You guys can see this. Okay. But yeah, hopefully you guys can see the screen. I want to go through, like I said, a little bit about predicting the products that we covered last time, just because I do think it's important being able to read it. And so for the people who aren't here, basically what you do is you just look for the different parts, and I'll go through the examples to hopefully make that make sense. And so we want to be able to make sure that we know how to use the solubility chart, because scientists, like I said, want to be able to make sure they can get the states. The states become important. So what's happening? So that brings up this thing called net ionic equations. Normally, the product of a double replacement is a solid inside of a precipitate. So if you look at the pictures, normally there's like a liquid part. If you can see, it has like a liquid portion. And then there's usually like a cloudy part, a part that's like a solid. If we were at school, we would have done this experiment and did each and every one of these things on the right, which is pretty cool. And that was well and good, right? They were able to combine these things and they are able to ice or see these different parts. So the question that scientists have is, could I potentially isolate that cloudy part? Because if they can isolate the cloudy part, then they can make it without needing this combination. They can make it themselves. This would give people the ability to pretty much make anything they want if they can isolate that equation. In order to do that, they need to create something called the net ionic equation. And it has a particular amount of steps. There's 6 steps, although it doesn't seem like 6 steps. But the first thing you want to do is determine the reactants and the products, the left-hand side and the right-hand side. And that's the reason why predicting products and then doing that charge balance is so important, because you have to have the left and the right side perfect. And then you want to determine the states: solid, liquid, gas, aqueous. Remember, if it's a solid, if it's a metal all by itself. Liquid, usually if it's just H2O, that's the only way to know, unless it tells you otherwise. If it's diatomic, it'll be a gas. And then if it's a metal plus non-metal, or it's ionic, it'll be aqueous. And so you want to be able to use those solubility rules. Then you want to balance it. A lot of people forget to balance it. and then they mess up. Then what you want to do is break down all of the AQs into different parts. And so you want to be able to make sure that we can kind of navigate that. Then you're going to cancel the parts that show up on both sides, and then you're going to rewrite it. And so I want to go over the steps because the steps can be a little bit tricky. I don't know which one to do. This one. Nope. Sure. No, I don't think I want that. All right, so I have these two examples. I'm going to look at the first one really quickly, and then I'll go over the worksheet. So here I have a H2SO4 or sulfuric acid, and it's going to get mixed with 2KOH plus K2SO4. They go to the products, K2SO4 plus 2H2O. This one happens to already be balanced, but we're going to look at it anyway. Because it's AQ, it's going to split in half. So anytime you see AQ, it's going to split up into two. And so here I have an H. And it's important to note that I don't just have one H, I have two H's. And then it's plus, you want to keep your polyatomic ions together. So it's going to be H plus SO4. Plus, the KOH is going to split apart. And this is the reason why balancing it is so important. I have one K in my equation, but if you notice there are two, there's a 2 coefficient in front, so it's going to be 2K plus 2OH. And that's going to go to the product side. And now the K2SO4 is going to break down, and it's going to be K, but I have two of them, so I have to bring those small numbers to the front. It's important to, once again, note your polyatomic ions because of the fact that those aren't, but for some reason you can't see it what I'm doing. It's not showing up. And so you want to be able to make sure that you, how come it's not going? You want to make sure that you are able to that you're able to, oh no, it's coming up. You want to be able to make sure that you're able to, Mr. Douglas, keep up with the coefficients that are in front. Now the H2O, because the H2O happens to be a liquid, we're not going to break it down. The only ones that break down are the AQs. And so because the AQ, or because the H2O isn't AQ, then it's going to be just H2O with the big 2 in front, and it's going to be a liquid. Anybody have any questions how I did that? How do I get the chat thing?
Nope.
Yeah, like hopefully it's pretty self-explanatory that if it's AQ, it breaks down. One of the hardest things that students don't understand is the small numbers, you have to bring them out front. And that's confusing for students who can't spot the polyatomic ions because they'll think that the SO4, you'll put the 4 in front, but the SO4 is only one of them. And so you have to think about that. All right, so now what we just did is this ionic equation part, if you see. I'm just gonna keep going through the blue part on the top, but if you look, what I'm about to do is cross out, they're called spectator ions because they're a part of the equation, but not really, or not part of the equation that we care about. So I have the left-hand side, the 2H plus SO4 plus 2K plus 2OH. And then on the right-hand side, I have 2K SO4 plus 2H2O. What I'm gonna do is cross out all of the parts that are on the same, or all of the parts that appear on both sides. So the SO4 appears on both sides, so I'm gonna cross that out. And then, so I'll cross out both of the SO4s. And the 2Ks also are gonna get crossed out because of the fact that they show up on both sides. You'll notice that in the example, they have the charges. It's up to you if you want to put the charges on. It doesn't really change anything. So what's left over? What's left over is the 2H plus 2OH goes to H2O. For some reason, it's not keeping up with what I'm doing, but oh no, it is. And so the product that we have at the end is 2H plus 2OH goes to H2O. And so that's how it works. I don't know, anybody have any questions on that? Like I said, I think it's pretty self-explanatory, but I can do another example. The other one is this reaction with copper sulfate. Yeah, is this example with copper sulfate. Is this example with copper sulfate and sodium phosphate, and then they switch. Once again, it's extremely important that you make sure it's not doing the thing. Oh, there we go. It's extremely important that you make sure that you are putting the correct states. Here we have AQ, so it's going to break up into CU, but because there's a 3 in front, we have to put the 3 plus SO4. So there's 3 of the SO4s. Once again, you have to make sure that you recognize those polyatomic ions. Plus, I have an Na3PO4, which is gonna give me 3 times 2. So I have 6 Na plus 2 PO4 is gonna go to, I have Cu3 PO4 with the 2, and I'm going to put the solid state so that we know that that stays together. Why did we keep the Cu3 PO4 with the 2? Is because, once again, if it has solid, liquid, or gas, you're going to keep it together. Plus, my sodium sulfate, my Na2SO4 is going to break down. So I'm going to have 6 Na plus 3 SO4. Anybody have any questions on how I did that?
Nope.
Now, once again, the ones that are on the left-hand side, we're going to cancel out with the right-hand side. So my 3 SO4 is going to cancel. My Na is going to cancel. And what that leaves behind is a 3Cu plus 2PO4. And the cool thing about the net ionic equations, if you did it correctly, balanced and everything, you don't have to balance it again at the end. The reason why I like it is because at the end, it's basically all done. You just bring everything down. I put the states back on. And so because the copper sulfate was AQ, then my copper at the bottom is also AQ. Because the Na3PO4 was AQ, then the bottom part is also going to be AQ. And then we have the solid that's left over. I don't know. Before I start going over the worksheet, anybody have any questions?
Mr. Douglas, what does this like really do in like terms of like real life, like doing this equation?
Yeah, so unfortunately, you mean like in real life? Like
Yeah,
what's the application for it?
Yeah.
So it doesn't have a purpose for us anymore. Yeah, I suppose if you like somehow destroyed all the technology that we have now, and if you somehow erased people's minds for the past like 20 years, this would be useful. But this, unfortunately, I usually do try to give you a real world reason why this is important. This part's not as important. You're never going to use it again. They're just trying to give you a historical understanding of how we got to where we are now. So like, let's say that you want to isolate like a chemical, right? So like I have this drug of some kind and I only want to isolate like a portion of it. This is how they used to do it a long time ago. They didn't have a way to isolate it before. Before, if there were chemicals that were mixed together, you would just have to take all of those chemicals. And even if there was like a bad one in that batch, I guess we're just gonna have to deal with that later. Like, you need the chemical now. It's kind of like what's happening right now with the hydrochloroquine, how, you know, the president says that people should take it because it helps with COVID-19. I guess ignoring the fact that it gives people heart problems and heart like defects later, I guess we're just going to deal with that later on. And so before, they weren't able to isolate the drugs or the chemicals. And so then they came up with net ionic equations, and now they're able to isolate it. However, today it doesn't have a real life application because we've already isolated them, if that makes sense.
Yeah. Okay.
And like anything that you would need to isolate, whoever gives it to you, they would have already isolated it. In college, if you are trying to do pre-med of any kind, or really science of any kind, they're going to make you take organic chemistry. And there's a special technique called the distillation. And a distillation is what they invent after this. So a distillation comes right after this, which allows people to separate chemicals out. And they wouldn't have been able to separate two substances without this knowledge, I guess. So yeah, unfortunately, in real life, this doesn't really have a use anymore because we have a database and we have everything else. If you ever do make a discovery, let's say you make a new drug or you make a new thing, you do have to do this net ionic equation thing. Because usually what it means is here we have copper 2 plus phosphate. What it means is that if I want to create this solid portion, I don't actually have to have copper sulfate, right? I can get copper anything. Does that make sense? I don't know if that makes sense.
Yeah.
as long as I have a copper that has a +2 charge at the beginning, I can choose any kind of copper, anything, plus it has to be a phosphate that has a -3 charge. And so as long as I have a compound that that has those two components, I can make this copper phosphate product, the solid one, assuming that's what I want. And this is how, like, if you want to know, like, how do people make like generic drugs, ones that are like significantly cheaper than like the one that costs like $1,000 or $1,000,000, that's how you do it. I can find a cheap version of copper, a cheap version of phosphate, put them together, boom, get the copper phosphate floating inside of whatever. Because if you look at the pictures, that's what's happening. They're floating inside of whatever it is, and then you just filter out the drug that you want. So yeah, I don't know if that,
Okay,
yeah. So like that's
that's
kind of,
cool.
yeah, it's a pretty cool thing that they were able to do. Like it opened up like basically pharmacy. Yeah, it's a big thing that they were able to do, being able to get this powder substance, and then kind of like manufacture whatever it is they need from any combination. And so it unlocked a lot of things, which is pretty cool when you think about it. Historically, anyway, that's what they're trying to do. And so here is the worksheet. You guys can take it out if you want to. Basically, I'm gonna go through. I won't do all of them. The answer key is on Google Classroom for you. There are some that you want to skip on page, the second page, problem 10 and 11, I believe it is. Just because it gets a little bit nasty. You can do them, but it gets a little nasty. Yeah, that's what I'll say. Problem 9 is kind of weird too. But I'll do like I'll do the first one, I'll do the fourth one, and then we'll see. Like I said, you have to make sure that you have that you are able to balance it. And so here for the first one, I have a sodium chloride that's aqueous plus a lead nitrate, and it goes to lead chloride plus NaNO3. And so if I am going to balance it, we want to start with the one that's the most complex. And so remember that this one, the NaCl, has 2 atoms. The lead nitrate, remember that we're going to keep those polyatomic ions together. So this one has 3. This one also has 3. And this one has just 2. So we're going to start in the middle. It doesn't matter which one we start with. So I'm going to start with the third one. We're going to compare the amount of PBs we have. The leads, we both have 1, so we don't have to worry about that. Now we have the chlorine, which has 2, and there's only 1 on the left-hand side. So I'm going to multiply the left side by 2. Now I have 2 NAs, so I need to multiply the right NA by 2. And I have 2 NO3s and 2 NO3s on the left, and so that's how I know that I'm done with the balancing. Now I just have to break them down. I have 2 NAs. I have 2 chlorines. Plus, I have 1 lead plus 2 NO3s. Like I said, you have to make sure that you keep track of those 2s and bring them out front. So plus 2 NO3s. It's going to go to PbCl2 with the solid. Why did I not break it down? Because once again, solid, liquid, gas, you're not going to break down. Plus, I have 2 Na plus 2 NO3. And so now we're going to scratch out the ones that appear on both sides. And then we're going to bring down everything into our net ionic equation. So it's going to be, I always like to do the order, the same order that's on the solid part, but you don't have to. You could put the 2Cl first if you want, but I always rearrange it. So I have 1 PB. I always bring the state back in, plus 2Cl goes to PbCl2 with an S. Questions on that?
No.
Yeah, like I said, I think it's pretty self-explanatory. I want to bring in, I'll do problem 5. I'll do 2 more, I guess. I'll do problem 5, and then I'll also do one of the ones on problem 12. So problem number 5 is important because of the fact that the reason why in the last class or lesson or whatever you guys are calling this, I wanted to make sure that we had our understanding of how to use the solubilities is because of the fact that we have to use these charts. And so I know that you guys weren't all here last time, but we have NH4NO3. Does anybody want to tell me what the state is? Looking at the chart. That'll help me like recap stuff. I can also just do it, I guess.
Is it aqueous?
Yeah, it's AQ, right? And the way that we did this, Danny, is the way that you determine the amount is what you have to do is see which part shows up in the chart. And the chart is on the resource sheet that's on Google Classroom. But as you can see, if you can see, Danny, that the NH4, it shows up in the first column, and then it says that it's always soluble. If something is soluble, that means that it's going to be AQ. If something is insoluble, then it's going to be a solid. And then we have to look for the exceptions. There are no exceptions, so this one is going to be AQ. Usually it's a pretty good rule of thumb. If one of them is AQ, the other one is going to be solid. But sometimes it doesn't work. If it doesn't work, then that means your equation doesn't work. There are some where they don't work like that. But that just means, I don't know, like to me, that's the reason why you have to do this, because sometimes it's pointless if you give someone something and then you realize it doesn't work. Anyway, so I have zinc phosphate. The phosphate, where are you? The phosphate is here. And so that's how we know that it must be a solid, because zinc is not one of the exceptions. And so we're going to break it down now. Oh, I forgot to balance it. Good job, Mr. Douglas. So we have 4 atoms here. I have 3 atoms here. I have 2 atoms here. And then this one has 5 atoms. So we're going to start at the, once again, the one that has the most complex. Here I have zinc. There are 3 zincs. So I need, I have 1 on the left, so I need a 3 in front. When I did that, my NO3 has 6 of them. We only have 1 NO3 over here, so we need 6. I have 6 NH4s. We only have 3, so I need 2. We have 2 PO4s. There are 2 PO4s, and so that's how I know that this one needs to be 1. The NH4 is going to break down. It has a 3 on the outside, so the 3 is going to multiply by the 2 and give me 6 NH4 plus my PO4, but there's two of them because there's the coefficient in front. Plus, my zinc nitrate is going to break down. Here I have 3 ZN plus 6, 2 times the 3, gives me 6 NO3. On the other side, I have 6 NH4s plus 6 NO3 plus 1 ZN3 PO4 with the solid. Then I'm going to cancel out the ones that appear on both sides, the 6 NH4, the 6 NO3. And so now I have 2 PO4 plus 3 ZN goes to the product side. Once again, I always like to rearrange it to put the positive one first, but you don't have to. You do have to put the states that way that we know, and then ZN3 PO4 with the 2 and make a solid. Questions on that?
Yeah, no questions.
Yeah, like I said, I think it's pretty straightforward. The only time if you struggled is if you don't know how to do the stuff we've done previously. I don't know how to read the I don't know how to read the chart. I don't know how to balance things. This part for problem number 12 is going to test our understanding of predicting products. Luckily, this one is double replacement, so we don't have to worry about determining which one. It's burning in my house. Sorry about that. Yeah, hopefully my house won't burn down. This one will test your ability to predict the products. And so to predict the products, we want to make sure that we realize that the BA and the NA2 are going to switch. And so you want to make that switch. So NA, and then we have NA and BR plus we have barium and the SO4. When we stick them together, what do we have to do? I have to charge balance them. And so here I have a +1 charge, -1 charge because of the columns. NA is in first column, BR is in the 7th column or 17th column. Barium is in the 2nd column, so it has a +2. And then if you check your resources sheet, you should have the polyatomic ions, which has a -2 charge. And so each one is going to cancel and give me 1 and 1. And so now we have to balance it like so. I have 3 atoms there. I have 3 atoms here. I have 2 atoms and then 2 atoms. And so we're going to start with the Na2SO4. You could have started with the barium bromide. It doesn't matter. So here I have 2 NAs. I only have 1 NA. So I need to multiply this by 2. We have 2 BRs, and there are 2 BRs over here. So that's how we know that we're done. Now I break it down. 1 BA plus 2 BR. So we're bringing that number out front, plus 2 NA plus SO4 goes to 2 NA. Oh, I forgot to do the states. This one, if you look at the chart, is going to be AQ. This one is going to be a solid. Na plus 2 BR plus 1 barium SO4 with the solid. Then we're going to cancel them out. The NA gets canceled. The BR gets canceled. And then we're going to bring everything down. The final answer, which is Ba plus SO4, goes to barium sulfate. Which is a really cool reaction. Barium sulfate is how you make crystals. It's really cool. If you ever see like crystals get created or made, it's really cool. This reaction is the precursor to how we're able to make all of these different products. Sean asked, what's the ramification of this? This net ionic equation thing and being able to isolate things and then reform the solid is how we're going to eventually get to making plastics. And once you make a plastic, that is when you can really, like that, manufacturing a plastic changed the world. Like it's hard to quantify just how amazing that was. Because now with plastics, you can basically mold anything that you want, right? Before, in medieval times, they had metals and you would have to give it to a blacksmith and he would have to make something. And once he formed your armor, he'd have to boil it back down to create it again. The cool thing with the plastic is that's our form of metal. We can create anything that we want. And we can recycle it and turn it into another plastic, which is cool. This is gonna give us the ability to basically make anything that you want. Fast forward that to today, what is a device that's revolutionizing medicine and revolutionizing pretty much anything is 3D printing, right? 3D printing, the ability to give someone a blueprint and make whatever it is you want. Yeah, that's pretty much all the examples. I don't know if you guys want me to do some more.
I think I'm fine. I mean, it's pretty self-explanatory.
Yeah, like I said, like in my opinion, I think it's pretty self-explanatory to me. Like I said, the only people who don't know how to do it is if you don't. This is me trying, Mr. Douglas. He's struggling. He was trying to get a Nintendo Switch. He can't get it. The struggle. I want to highlight the answer key. Oh, nope, that's not the one. The answer key that I posted as well. So if you want to see all the processes that I went through, I tried to indicate once again 10 and 11. You should probably skip. But just trying to show you for the people who might struggle with predicting products, which can be a little tricky. But yeah, this is the chemical reactions part. This is the last little bit. Next week might be a portion where you might want to skip because next week is just going to be for a review that will cover everything. But yeah, that's pretty much it. The really cool thing about this is this will set us up for next unit, and next unit will be very math heavy. Like it's just basically math. Because now the scientists know how to put equations together, they want to be able to use it so that now they can create anything they want. Now they have to ask themselves how much, right? Because before they were just mixing things together and then just getting random amounts and they just have to take that. But what happens if I want like specific amounts, like 50 pounds, I want 60 pounds, 70 pounds, I want a specific amount of product. That's what they're going to try to do is figure out, instead of it just being random amounts that I get at the end, I want to make it so I can determine and predict the amount that I need at the beginning and the amount that I'm going to get at the end. And that becomes super powerful, where chemistry is going to help manufacturing and really make real world applications possible for businesses, which is pretty cool. Yeah, does anybody have any questions heading into next week or anything else? I'm not sure if you guys are going to be there for Friday's thing.
No, I think I'm all set.
Okay.
Okay. Especially because you guys have just been coming. So I don't know if that's useful. I think it'll mostly just be a recap. One of the things that I will say on Friday is if you're thinking about double blocking your science, you'll want to let me know. I know that I told you guys before about creating a note in when you guys sign up. If you're thinking of taking an AP level class, if you could just send me an email or just send me a note somewhere that's what you're thinking about doing, because what I'm hoping to do, they're not going to get to the sophomores until at least next week, if not the week after that. But I want to compile a list for your guidance counselors just to make sure that you get the classes that you want. That's pretty much what next week is for. Like I said, next week is a little bit of a content light week, just because it's literally just going to be a review thing. Yeah, if there aren't any questions, I don't know. I imagine some people might have questions about quizzes and how do we test the material. Like I said, it's mostly just for learning purposes. I can put together a quiz for you guys and you can just take it and then you just, I don't know. I don't have a problem if you take it and then it takes the place of a quiz that you did, I guess. Yeah, I don't have a problem with that. Most of my honors classes, though, thought they are doing pretty good on their assessment scores. But that is something that I can offer for the people who have it. I don't know. Is that something that you think students would be interested in?
Yeah, there's some kids in my class that probably need that sort of opportunity.
Yeah, like I said, it might not be like, yeah, like I just feel, I hope to give you guys as many opportunities, not for the people who are struggling, but people who want to increase their grade. I hope that they can take advantage of some of the stuff. But that's pretty much it. Yeah. Anything else before we sign off?
No.
Good. All right. Well, that's pretty much it. Review for next week.
Okay. Thank you.
Yep.
Thank you.
Oh yes, wash your hands. How do I end this? This one?